Let's do a few examples of integrating one-form fields over paths. Consider, for starters, the integral of the one-form field alpha given by z squared dx minus 3xy dz along the straight line path from the origin to the point 2, 4, 6 in 3D. Now, we remember how to do this. The integral of alpha over this path can be accomplished using an explicit parameterization, gamma of t. So what would you pick for such a straight line path? Well, I think you would probably pick the constant speed path given by gamma of t is t, 2t, 3t. Those are the x, y, and z coordinates, and t is going to go from 0 to 2. Always be explicit in the bounds on your parameters. Now, what do? We have to integrate z squared dx minus 3xy dz. The first step is to substitute in the x, y, and z components of gamma into this one form so that we get the integral as t goes from 0 to 2 of 9t squared dx minus 6t squared dz. Now, I need to feed a vector to that one-form field, and that vector is going to be the derivative of gamma, where gamma prime of t is the constant vector, 1, 2, 3, because this is a constant speed path. Okay, so when I feed that vector in, what happens? Well, dx looks at that and pulls out a 1. dz looks at that and pulls out a 3. So what we get in the end is the integral as t goes from 0 to 2 of 9t squared times 1 minus 6t squared times 3 dt. That winds up being the integral of minus 9t squared. That yields minus 3t cubed. As t goes from 0 to 2, that evaluates to our final answer of minus 24. And that's it, we're done. But remember, this formula for the integral of the one-form field is independent of the parameterization. That means if we used a different path that didn't have constant speed, but which was variable speed, but which traces along the same curve, let's say gamma of t is t squared, 2t squared, and 3t squared, so that we start off walking slowly and then speed up as t increases, well, this should give us the same answer. Now, in this case, t does not go from 0 to 2. It goes from 0 to root 2, so that we end at the same point. Let's follow that same computation. Let's integrate, substituting in t squared, 2t squared, and 3t squared for x, y, and z. That gives us the integral as t goes from 0 to root 2 of 9t to the 4th dx minus 6t to the 4th dz. Now, when I compute the derivative of gamma, I don't get a constant vector. I get 2t, 4t, 6t. dx looks at that vector, pulls out a 2t. dz looks at that vector, pulls out a 6t. In the end, I get the integral of 9t to the 4th times 2t minus 6t to the 4th times 6t dt. That is really the integral of minus 18t to the 5th, which yields minus 3t to the 6th. I evaluate that as t goes from 0 to root 2, giving in the end negative 24, as it must. You've got to get the same answer if you parameterize the same path. Let's turn to a different example, this time integrating along a loop instead of along a path. Consider the rotational one-form field, alpha, given by minus y dx plus x dy. Let's integrate that along a circle of radius r based at the origin. Now, the same formula applies. We just need to parameterize this path. Let's take the typical circular parameterization, r cosine t and r sine t. That is giving us a counterclockwise path as t goes from 0 to 2 pi. Now, what do we need to do? We need to integrate minus y dx plus x dy. Our first step is substituting in r cosine t for x, r sine t for y. This gives us the integral of minus r sine t dx plus r cosine t dy. Now, what do we feed to that one-form field? We have to feed it the derivative of gamma. That is the vector minus r sine t, r cosine t. When I feed that in, the dx sees that, pulls out a minus r sine t. The dy sees that, pulls out an r cosine t. That gives us the integral. As t goes from 0 to 2 pi of r squared sine squared t plus r squared cosine squared t dt. We see clearly the common factor of r squared. What's left over is a sine squared plus cosine squared. Hooray, that goes away. We're left with the integral of the constant r squared as t goes from 0 to 2 pi. That gives us a final answer of 2 pi r squared. Simple. Now come back to this example after you have viewed chapter 6, and you'll see an easier way to get this answer immediately. Now, there's one last thing I want to point out. What do you think would happen if we reversed the direction of this path? If instead of t going from 0 to 2 pi, we went from 2 pi to 0 and went in reverse? Well, if you follow what happens in our computation, that would have the effect of reversing the bounds on t. And you know back from single variable calculus what happens when you flip the bounds of integration. You get a minus sign. This points to the more general truth that when you reverse the orientation on your path gamma, whatever gamma might be, then what you get is minus what you get with the original orientation. So in multivariable calculus, in field calculus, the effect of reversing orientation is to get a minus sign in front of the integral. That is the generalization of that well-known fact from single variable calculus.